Thanks for having me today. I want to present some work I've been doing on examining the prospects of BECS for observing subparsec black hole binaries. I think this follows on very nicely from Jenny Green's talk earlier. And this has begun to emerge as a potential additional use case of BECS out of the demographics working group. So to briefly touch on the science case here, so we're talking about the potential for the first direct electromagnetic evidence of a subparsec binary. If in theory, if a population of binaries could be observed and their masses and orbital parameters estimated, you could begin to constrain the processes involved in decay and merger models, and that has broader implications for modeling evolution on a galactic scale. And of course, you've got the obvious synergy with gravitational wave facilities. If you had a sample of binaries that you could observe, you could begin to improve predictions for the gravitational wave background and break some of the model degeneracies inherent there. So the key thing here really is that only VLBI has the resolution to directly resolve subparsec binaries, which are going to have characteristic separations on the order of micro-arc seconds. So the key questions really are, could BECS detect a supermassive black hole binary? Cannot BECS observations enable orbital parameters to be constrained? And how can we identify promising candidate sources in time for the mission? So there have been some works predicting the number of observable systems with VLBI. A key one from Durazio and Loeb stands out, and this figure is generated using data from their paper, and it shows an estimate for the number of observable sources with the conditions that the angular separation is greater than the array resolution, the observed orbital period is less than 10 years. And to provide some context, I've plotted the angular resolution of BECS on here, and on a BECS sort of ALMA baseline, we could expect sensitivity of around 1 millijansky. So the predicted number of sources is very low, but increasing the maximum allowable observable orbital periods increases the number of predicted sources. Now, of course, there are significant assumptions in developing these models, but they do probably show that binary observation is likely at the edge of ground and BECS capability. But if we dream for a second that BECS or a high-resolution ground array could detect such a system, let's examine what would be needed to confirm a detection. So one challenge is, how do you confirm that what has been observed is indeed a binary? I think you can split this into two key questions. So the first is, are the two sources, are they both supermassive black holes? And here you're looking for more typical spectra and polarization signatures. Maybe there's some launching of jets, and you also have the circumstantial evidence of their location within the center of a known AGM. And then I think the key one is, are they exhibiting orbital motion? So can you observe across multiple sort of epochs, detect relative motion, discern some sort of curved trajectory, and then begin to estimate orbital parameters? And the figure on the right here is an analytic expression to estimate the minimum number of observations to detect curvature in a observed trajectory, considering the uncertainty in the position estimation. And this is sort of postulating that as a first step, the null hypothesis to be rejected is, instead of an orbital motion, there's some sort of linear relative motion going on of the two sources. And you can consider some scenarios of potentially erroneous detections of this form. So I think this is the first step in the process of detecting orbital motion, particularly when there's really short orbital arcs observed, and a useful metric for planning future observations. So you can see that for annual observations in this figure for BECS with the solid lines, what orbital periods and angular separations can be confidently confirmed to be exhibiting a curved trajectory with certain numbers of observations. So I've designed an orbit fitting approach using a Bayesian Markov chain Monte Carlo method. This has extensive use in fitting orbits for binary stars and exoplanets. And I've implemented a post-Newtonian orbit propagator to do this. And this is up to 3.5 PN. But there's currently no spin effects included here. But I have included the effect of the relative light travel time from the two sources at redshift. And this is actually an order of magnitude higher effect on the observed position than the spin effects on the relatively short timescales we're observing on. So yeah, this Bayesian method is very useful for understanding the posterior distribution and what constraints, if any, we can pull out of some observations of such a system. So to dive into BECS binary detectability, and very much thanks to Daniel and Angelo for first producing this plot, and it depicts the required total flux density of a source for BECS to discern a double Gaussian from a single Gaussian, and also from the signal of the primary alone. So modeling the binary here as two Gaussian sources. So W1 is the angular diameter of the primary component, and then the detectability for regions with varying angular separations and flux density and size ratios is then plotted. And then the conclusions from this you can draw are detection is easier when the primary is more compact, the secondary is sufficiently separated, and there's also a preference for lower mass ratio systems if you assume that the flux density is distributed proportional to the mass. And some of the key numbers here are below 40 millijansky, there are no detectability regions. That's sort of the bottom line for what would be possible with BECS. So I've implemented a simulation pipeline to explore this binary detectability with BECS more, and also to test my orbit fitting approach. So starting with an image model, considering this dreamlike scenario of a visual telescopic binary detection. It's a binary Gaussian model with this post-Newtonian orbit propagation. I'm simulating observations with BECS, assuming the northern ground array with ALMA participating, fitting a binary Gaussian model to the amplitudes and closure phases of that data, and then extracting estimated positions from that. So then I'm assuming we can do, let's say, 3 annual observations with BECS, so sampling the position across 3 separate sessions. So assuming a slightly extended BECS mission here, but not beyond the realms of possibility. And then I'm fitting an orbit to the observed positions with this Markov chain Monte Carlo method. So looking at a couple of example cases just to demonstrate this working and some of the trends we may expect to see. So here we have perhaps the simplest form of orbit you could imagine. So it's a circular face-on binary with a very short orbital period, only 5 years. Absolutely ideal for BECS observations, as you'd be able to sample a very wide arc of the orbit, although the separation and flux density are down at the limit of BECS detectability and resolution. So the false alarm rate here is near 0 because we've sampled this very long arc, and this false alarm rate number is describing the probability that the observed trajectory could be attributed to this linear motion rather than orbital, considering the astrometric uncertainties in the model fitting. So this is an equal mass binary, but I've slightly distributed the flux density unevenly between the 2 sources to break the degeneracy you get in the visibility data when you've got 2 identical Gaussians like this. So considering the posterior distribution briefly, the total mass is really well constrained. This is directly related to the orbital period, so you'd expect that. But the mass ratio Q is degenerate somewhat when you're just fitting the secondary orbit with respect to the primary in this relative astrometry way. The orbit shape is really tightly constrained. Again, we've got this long arc sampled. But in terms of sort of the angular parameters, there's a slight preference for low inclinations, but the posterior is very wide. And again, I think you'd expect this with no other constraints on the sort of inclination prior. Many combinations of semi-major axis eccentricity and inclination would produce the same projected 2D shape on the sky. So just the second case, just complicating this model somewhat. We're still considering a face-on binary here, but I've introduced some eccentricity into the equation. And also it's a longer orbital period now, so 20 years. So as I was saying earlier, there are more likely to be more of these longer period orbits that you could potentially observe. And this makes sense if you consider the residence times of binaries at different separations. So we're now sampling a shorter arc of the orbit. This false alarm rate is not negligible anymore, but still quite small, as the orbital field is better than the linear. And this would obviously keep increasing the longer the orbital periods get, as the arc would get shorter and the curvature less discernible. And this is still only using this linear motion model as a null hypothesis. I can absolutely imagine false alarm scenarios that exhibit non-linear motion that are far more tricky to discern an orbit from than this. But as a first step, this is what I'm thinking about. And then again, the posterior distribution. So total mass is even better constrained than for the first example, as we now have this eccentric orbit. You have the sort of varying velocity at each observed position, and this provides additional constraints on the mass. And the median values of the 2 individual masses are actually quite a bit closer to the truth. I'm still exploring why this mass ratio begins to show a tighter constraint for the eccentric orbit. The orbit shape is a bit less well constrained now. Again, unsurprising. Beyond our 3 observations, the orbit can deviate really significantly from the truth. And the inclination still is a very wide posterior. And I've run additional cases with the same eccentricity and begin to introduce inclination, and you do get some fits that actually deviate far more drastically from the truth. Really highly eccentric orbits with much larger black holes, resulting in a smaller semi-major axis. And I'm currently exploring more and more test cases to try and understand these trends in the fitting better. So now this is all very nice, but obviously the key question is how how do you identify promising candidate sources in time for launch, if any exist? And to my knowledge, we currently have no really, really good sources that warrant valuable BECS observing time. But if we just summarize a couple of the key methods for identification, and one that stood out to me is the Nanograv collaboration recently released a paper presenting the results of targeted searches for continuous gravitational waves. And this is amongst known AGN with QPO evidence. And essentially their method involved introducing priors for circular orbits with periods and positions on the sky estimated from those sort of light curve surveys. And they use this data to fit the PTA data for the remaining binary parameters. So, they calculate the base factors to demonstrate statistical significance. It's of course very low, but I think it's at this stage it's the method perhaps rather than the sources themselves that are particularly interesting, and you'd hope this would only get better as pulsar timing improves in the future. Although having said that, the predicted separations and redshifts for the two sources they pulled out of the data are tantalizingly within BEC's capabilities, so who knows. Vera Rubin Observatory is coming online very soon, had the first light event recently, expected to contribute significantly to these periodic AGN variability studies. Obviously, difficulty here is these methods are highly susceptible to these false alarms due to the intrinsic variability of the source. And then in terms of VLBI, there have been proposals for using absolute astrometric data to identify oscillations that could be attributed to orbital motion. And then you also have the jet morphology and precession that could also be signs of a present binary in the system. So obviously none of these methods are conclusive. This conversation wouldn't be as interesting if they were, but we're looking to build a body of evidence to determine whether a source is worthy of valuable BECS observing time. And actually those of us in the demographics group had an interesting presentation from those behind the Ether database last week, and they're beginning to build up a repository of binary candidates with plans for follow-up radio observations, and that will no doubt play a key role in this activity of trying to identify a candidate source. So just to summarize, BECS has the theoretic performance necessary to provide the first direct detection of subparsec binary. The challenge is obviously identifying relevant candidate sources, and if they can be found, it'd be arranging sufficient observing time to detect orbital motion in the busy schedule. Obviously, this is not BECS's primary science objective, but you then can consider BECS as part of a long-term multi-instrument observation of binary candidates, perhaps with future spaceborne VLBI systems. So we've constrained BECS's binary detectability, which will be useful if we can begin to identify some targets. We need this total flux density of greater than 40 millijanskis and a minimum separation of 2 microarc seconds, although at this level the source will be unresolved. Begun to demonstrate some of the trends in what we can do in terms of fitting orbits to this data. The shape itself and the total mass is really well constrained, even for orbital periods up to 20 years. But things like inclination are less so. But perhaps there's also some interesting things you could do with introducing priors and inclination, looking at flux density variations due to Doppler boosting and things like that. So in terms of next steps for me, I'm going to further explore these BECS binary detectability with more test cases, hoping to get some time on TU Delft's supercomputer to do this, as computation's been my main issue so far. I'd like to dive into the source identification activity in a bit more detail, perhaps get involved in some of these efforts, and also begin to complicate this image model somewhat. It's a very nice, clean double Gaussian at the moment. Maybe introduce some more realistic features going forward. And yeah, the paper presenting this is currently in preparation, and that also has a bit of a focus on defining the requirements of a future spaceborne VLBI system that would be, let's say, specifically designed for such activities. But yeah, that's all I've got. Thank you very much. If there's any questions, I'd love to hear them.
Thanks so much, Ben. Why don't we go ahead and get the next speaker queued up? I think it's clear that you want to take the photon ring to Gondor. And we have time for one very quick question from Marshall. Take it away.
Hi, this will be a quick question, although not necessarily a quick answer. So I've been doing a lot of work looking into the numerical relativity models and spin flips. The fact that you have a fairly large spin angular momentum can do really weird things, I think, to the orbits. They can actually make orbits like not decline, not constant periodicity, all that kind of stuff, because you can transfer angular momentum between the spin of the black holes, the 2 black holes, which don't have to be aligned, of course, and the orbital angular momentum. And so there's some really interesting things going on there, which may not happen all the time, which can happen. And I think this is an area we really need to look into. It might explain and even like why sometimes things look periodic at some times and not at others. But there are spin flip, there are numerical stuff where it really does look like the orbit has increased in size a little bit because it's taken that angular momentum from the spins. And that's just to me kind of amazing.
That's interesting. Yeah.
And I suspect you're not modeling that at all. I suspect you're not introducing spin here at all in the orbital dynamics.
No, I completely ignored spin. I sort of did a first order estimation of how much that would affect the observed position in, let's say a 10-year period. And it's far lower than, let's say, would we ever be able to detect with a Bex-like instrument. So I ignored it for now.
But that's saying you're pretty far from merger. As you get closer to merger, it gets more
Yeah, okay, that's true.
noticeable. All right, thank you.
Yeah. Thanks.
Okay.